Hello and welcome. Today, we're going to pull back the curtain on solar power. And we're going to do something a little different. Instead of just talking about it, we're going to conceptually build a complete solar power system right here from the ground up. Ready? Let's get into it. I mean, think about it. It seems like magic, right? How do you take something you can't even hold, sunlight, and turn it into the actual electricity that can power your life? Well, I promise you, it's not magic, it's science. And by the time we're done here, you're going to know exactly how it works. And that's it. That's our entire roadmap for today. We're going to look at 4 essential building blocks, check out the 2 basic ways to wire them up, and then cover the most important rule of all, safety. So yeah, let's get our hands dirty. Conceptually speaking, of course. Okay, before we pick up a single tool, we need to get our heads around the one scientific principle that makes all of this possible. It's called the photovoltaic effect. Now that sounds complicated, but it's not. Basically, when sunlight hits the special silicone inside a solar panel, it knocks electrons loose. And that flow of electrons, well, that's electricity. It's the scientific spark that starts this whole incredible journey. All right, every project needs a toolbox. And for our solar build, our toolbox has 4 absolutely essential components inside. Let's meet them one by one. First up, the star of the show, the solar panel itself. This is our energy collector. It's doing that photovoltaic magic trick we just talked about, creating what's called DC, or direct current. But here's a super important detail. A panel that's meant for a 12-volt system actually puts out more like 14 to 18 volts. And that little bit of extra voltage, it's absolutely crucial for our next component. Next up, we need somewhere to put all that power, right? For when the sun goes down or it's a cloudy day. That is the job of the battery. It's our energy reservoir. Just think of it like a water tank. The panel fills it up all day long, and you can draw from it whenever you need to. This is what gives you that stable, reliable power, and it's a must-have for any off-grid system. Now, you can't just hook a panel straight to a battery. Remember that extra voltage we just mentioned? It would just cook the battery, overcharging it and destroying it. That's where this little genius device comes in, the charge controller. It's the traffic cop of the whole system. It sits between the panels and the battery and carefully manages the flow of energy. It makes sure the battery charges safely, and it also stops you from draining it too much, which can be just as damaging. And that brings us to our final core component, the inverter. You see, most of the things in your house, your TV, your fridge, your laptop charger, they don't speak the low-voltage DC language of batteries. They speak high-voltage AC, or alternating current. The inverter is basically a translator. It takes that DC power and converts it into the AC power that all your standard appliances know how to use. So let's trace that path of power one more time, just to lock it in. Sunlight hits the panel makes DC power, that power goes through the controller, which safely fills up the battery. When you need power, it comes out of the battery, goes to the inverter, which translates it into AC power, and finally, your appliance turns on. That's it. That is the complete journey, from the sun all the way to your socket. Okay, so we have our 4 core components laid out on the table. Now, how do we actually connect them? This is where the blueprint comes in. And there are really 2 fundamental ways to wire things up. And you've got to know the difference. We're talking about series versus parallel wiring. And honestly, the analogies you see here make it super easy to grasp. Series wiring is like stacking ladders to climb higher. You connect the panels end to end, and the voltage adds up. Parallel wiring is like putting those ladders side by side to carry more weight. You connect all the positives together and all the negatives together. The voltage doesn't change, but you increase your capacity, or what we call current. So let's see a real-world example. Let's say you need to run a 24-volt system. You don't need to go out and buy special 24-volt panels. Nope. You just take 2 regular 12-volt panels, wire them up in series, and boom, the voltages add up, and you've got yourself a 24-volt system. Simple as that. But what if you're totally fine with 12 volts? You just need more juice, maybe to charge your batteries faster. Well, that's when you wire in parallel. You take those same 2 12-volt panels, hook them up in parallel, and you still have a 12-volt system, but now you've got double the current, which means double the power-producing capacity. See? With these 2 simple blueprints, we can start to build some very different systems. And that's what's so cool about this. Using the exact same components and these 2 wiring principles, we can build 2 totally different kinds of solar systems, each designed for a very specific job. On one side, you've got your off-grid system. This is your personal, totally independent power station. It uses all 4 components we've talked about, the panels, the controller, the batteries, and the inverter. You are your own utility. But on the other hand, you have a grid-tied system. This one actually partners up with the utility grid You don't even need batteries or a charge controller because the grid itself acts like a giant infinite battery. And get this, any extra power you make can get sent back to the grid, and the utility company might even pay you for it. Okay, we've designed our system, we know how the parts work and how to connect them. But before we even think about flipping a switch, we have got to talk about the single most important rule in all of this: safety. Electricity, even the low voltage kind, is no joke. It demands respect. So think of this as your safety cheat sheet. Fuses and switches are your first line of defense. If something goes wrong, they cut the power instantly to prevent fires. Grounding is an absolute must. It gives any stray electricity a safe path to the earth, instead of through you. And then you have devices like RCDs or GFIs. These things are literal lifesavers. They detect the tiniest faults and shut everything down before you can get a dangerous shock. And if you're ever tempted to think, it's only 12 volts, what's the big deal? Just read this quote. See, in a battery system, it's not the voltage you worry about, it's the amperage, the current. And that can be incredibly high. A short circuit can unleash hundreds of amps in a fraction of a second, and that is more than enough to be lethal. This is why safety is everything. And a huge part of being safe is something people often overlook: the cables themselves. You can't just use any old wire. The cables from your panels have to survive sun and rain for decades. Your battery cables need to be super thick, like seriously beefy, to handle all that current we talked about, and all the other wires have to be perfectly sized for the job they're doing. And let me be perfectly clear about this: using cables that are too thin is one of the biggest and most dangerous mistakes you can make. Not only does it waste your precious solar power by turning it into heat, but that heat can actually build up, melt the wire's insulation, and start a fire. So getting your cable size right isn't just about being efficient, it's about keeping everything, and everyone, safe. So there you have it, the 4 core components, the 2 ways to wire them, and the essential rules of safety. You now have the complete conceptual blueprint for taking pure sunlight and turning it into usable power. So the only question left is, what would you do with it? What would you power with the sun?